then we're gone for a few days, and we're going to have a test next week, right? The test next Friday. Friday's the test day, so we will spend one day reviewing for that test, getting ready. We are going to have, so we're going to have one more hour-long test before our final exam. The final exam is something separate, and we're in very good shape. We're very comfortable. I'm not sure how we'll finish out the course. I had planned on maybe going a little bit beyond chapter 6 into chapter 7. I'm not sure yet about that. Let's see how these next couple days go. I'm not going to like shove a bunch of stuff down. Cover a whole bunch of stuff in the last couple days, so you can feel good about that. Chapter 7 is sort of optional, so might be fun to do, but maybe we won't have time. We'll see. All right. And okay, so let's. I really like this next theorem coming up. Theorem Larky, theorem 13, and so we're going to dwell on it for a little while before we do a problem. I think it's also, it pulls together a lot of what we talked about in this chapter in this almost magical way. It gives us this result where we're basically just going to have a formula in the end, where we can plug into a formula and get exactly what we want. But I want to try to make an effort to bring that formula to life a little bit. All right. So just some stuff we're already familiar with. I've got on the board, but we're starting from an n by n matrix, and we're looking at a matrix equation of the form AX equals B. Okay? And remember, you can think of that as a linear transformation, right, from Rn to Rm. So X is a vector in Rn to domain space. A times X is a vector in Rn, the codomain space. And what if AX equals B has no solution? That's the whole issue here. Can we find our best, our closest possible value to B? Can we get AX as close to B as possible, even though we can't hit B exactly? And so we talked about how AX equals B can be written as B minus AX equals 0. If there is a solution, then the length of B minus AX is 0. And if AX is just close to B, B minus AX might be 0 but small. So a least square solution is what it means. What it means is that we have an x hat, we'll call x hat, with this symbol over the x, our least square solution. It means the length of B minus AX hat is less than or equal to any other possible value for B minus AX, where x is any vector in the domain. So looking at all possibilities there. Now just some more notes here. So like if we think of this as a transformation from Rn to Rn, of course AX is in Rn, B is in Rn, B minus AX is also in Rm. So while the x's are in the domain space, the thing we're taking the length of here, those are vectors in the range space, right? Because they're outputs of the linear transformation. This is also where the column space of A sits. So I'm sort of trying to just draw a distinction here between X and what's, I don't think we need the null space here, but the null space of A is here. We're also going to talk about the transpose of A little bit. And when we talk about the transpose of a matrix, everything's reversed. So just as we're comparing Rn and Rm, Rm is where the null space of the transpose matrix sits, and Rn is where the column space of A transpose sits, just for the record. to AX equals B. And the words least squares don't have that much meaning to us. It just, when you go through an actual calculation of this type of thing, you end up with squaring a lot of numbers. That's all. That's really our only observation we got to make about that. So that means that x hat is a least square solution. B minus ax hat is less than or equal to b minus ax. So I'm just copying what's on the handout there in that definition of least square solution. But I just wanted to impress the fact that when you see this ax here, that really stands for every element of the column space of A. So it just helps me to think of that ax as x takes every possible value. Ax is going to give us every single element of the column space of A. So we can reword this inequality statement using column space of A. We could say AX is as close or closer to the vector B than any other element of the column space of A. That's kind of what that inequality statement is saying. I'm going to start talking about the hat. Write one more thing down. I'm going to figure out where to put it. All right, so let's look at the theorem 13. So let MA be an m by n matrix, again, let B be an Rn. Consider the equation AX equals B. We probably have no solution. I mean, if there is a solution, the least square solution is a solution, and there's nothing really for us to talk about. So it's usually just interesting for us when AX equals B has no solution, is an inconsistent system. So X hat is a least square solution to that equation if and only if X is an actual solution to this matrix equation. A transpose AX equals A transpose B. So this weird approximation thing, this X hat, we can find as an exact solution to this other kind of matrix equation. We're going to talk about why that's true and go through the steps of this proof. I love that formula. I just think it's so cool. All right? So let's talk about the proof of that statement. And then we'll apply that formula. Much more below this. So it's a if and only if. So you got to show the implication in both directions. The only if part means we start out assuming X is a least square solution. So X is a least square solution to AX equals B if this statement is true for every X in Rn. So the X's are in Rn, but the AX's are actually in Rn, as well as the B's and the B minus AX's. So let B hat be the projection of the column space of A onto B. So if you go back to our 6.3 theorem 8, where we had a y, we could say take the vector B, and then we get a B hat plus C. And instead of W, we can talk about the subspace that's the column space of A and the perpendicular complement of the column space of A. So that's where we're applying this. We're going to apply this previous theorem 8 from 6.3. And I guess while I'm here changing things, B hat is the closest point in the column space of A to the, sorry, I'm a little below the screen here, to the vector B. So we're just talking about B in the role of Y from that previous scenario. So I'm turning the page. So again, tried to prepare us so we're not too shocked with this statement. B hat is the closest point in the column space of A to B, right? That's 6.309. And by the definition of least squares solution, no point in the column space of A can be closer to B than A x hat, this guy right here. And since B is unique, or B hat is unique, sorry, B hat is unique, it has to be true that the B hat is AX. All right? So this guy is unique. It's in the column space of A. It's the closest point in the column space of A to B. And so basically what this then says is this A x hat has to be the thing we're calling B hat, the projection of B into the column space of A. Now I want to draw a picture of this too. It's all symbols right now, and I need some space, so let's stop. So we're just going to look at our M, which is the codomain of the linear transformation, or the range space. This is a picture in the range. And I'm going to oversimplify things because I can't draw M dimensions. And I want to draw some perpendicularities, so I'm going to cheat a little bit and make my picture very simple. I'm going to pretend that the column space is just that horizontal plane in the origin, like the xy plane. I mean, it's probably not. It's some subspace, but let's just pretend. So sitting in here are AX's for all possible values of x. X itself is in a different space, but AX is in this column space A, right? And AX hat is one particular element sitting in the column space of A. And now where's this vector B? The way I imagine B is just, it's out somewhere else, right? And that's the whole issue here. B is not in the column space of A, so AX equals B has no solution. Right? That's sort of a picture of the fact that AX equals B has no solution. Right? And what we're saying here is if we project B down perpendicularly into the column space, and the notation we have for that is B hat when we project that down, it's got to be this A x hat creature. If the x hat exists, we're assuming the x hat least squares solution actually exists. Okay, so to me that's the kind of the picture for what's going on here. And now B minus B hat, which is sort of like this Z. Actually the exact same role, right, from this equation, B minus B hat, sits in the column space of A. In other words, B minus B hat must be orthogonal to the column space of A. And that's by theorem 8.6.3. Again, I'm just referring back to that guy, right, from an earlier section. And now I'm just rewriting, kind of reiterating this. B is B hat plus B minus B hat. This is the same as Z, what we used as Z notation before. So this is a projection into the column space of A. This is an element of the perpendicular complement of the column space of A. And since the column space of A perp equals the null space of A transpose, right? Now, we haven't really been thinking about that a real lot, but that is a result from theorem 3 from 6.1. All right, so you got to go back and look at that and go like, what? It actually was easier to talk about that in terms of the original matrix first, and then we kind of changed the language to the transpose. But that is a result. We know B minus B hat is in the perpendicular complement of the column space of A, so here's the cool step, I think. So that means that's just saying B minus B hat has to be in the null space of A transpose. And now we're just going to write down what that means. Like, to me, this funny theorem is what's kind of helping us make this equation work here, all right? And to say B minus B hat is in the null space of A transpose. That means if you take A transpose times B minus B hat, so A transpose you can multiply by m-dimensional column vectors, you get 0. So A transpose times B minus, instead of B hat, I can write AX hat. We just showed that AX hat has to be equal to B hat. And now I just distribute and take the negative term over to the other side. And what do I have? I have A transpose B equals A transpose A X hat. So X hat is a solution to this equation. And that was the equation in the statement of the theorem. But there are a lot of pieces to this, right? To bring it all together. Now, we're still not done with the proof. That was only one direction of the logic. And I'm just going to go much quicker through the second half because it really does just sort of reverse the logic we just went through. So suppose you know X hat is a solution to that equation. How do you know that every solution to this equation, matrix equation, must be a least squares solution? And you just kind of work backwards through these steps. X hat is a solution, so we can say this, so B minus A X hat is in the null space of A transpose, so that means B minus A X hat must be in the perpendicular complement of the column space of A. So we know that B is equal to AX hat plus B minus AX hat because that just works out, right? If you combine like terms. And if we know B minus AX hat is in the column space of A perp, and we know AX hat must be in the column space of A, because A times anything is in the column space of A. So these are like two separate statements that have to be true. By the uniqueness, one of our theorems, we made a point of saying this decomposition was unique. There's only one way to do it. So by uniqueness, the AX hat actually has to be the projection of B onto the column space of A. And A X hat is the closest vector in the column space of A to B. That means X hat is the least squares solution. Boom. There's. I think you got to think about it a little bit. So I don't know. This isn't something where I'd be sitting there saying, "Oh yeah, I got it. I see it." But I mean, all the steps are there, all the pieces are there, and I think it's very accessible for you to be able to think through the logic. But now, if you're like, what the heck is going on? Let's do a problem. Because I think just the statement of what we're saying, I can see how you guys might think it's not obvious. Does anyone still need a 6.5? Is anyone realizing they need a 6.5? Can I give you both 6.5? So I'm going to turn this off so we can do a problem. what, A8 is 3 by 2, right? B is going to be 4, 1, 3. And we're going to find the least square solution. You can check on your own that AX equals B is inconsistent. It has no solution. And that's what makes this interesting. Okay, we're trying to find a vector X that comes close. And so what are we going to do? We're going to solve that equation from the theorem. And it looks kind of overwhelming when you see that equation with transpose, but I hope you realize we're just taking AX equals B, which we've written down like a million times in this course so far, and we're just multiplying by A transpose on the left-hand side of both sides of that equation. So isn't that, I don't know, you just don't think about it. Like, we're going from matrix equation, a system that has no solution. If we just multiply by A transpose on the left on both sides, there must be a solution. There is a solution. There's always a solution. So the calculation, we got to figure out what A transpose A actually is. So A transpose is going to go 1, 3, negative 2, negative 1, 2, 4. I'm interchanging the rows and columns, right? So A transpose is actually going to be a 2 by 3 matrix, while A is a 3 by 2. Negative 2, negative 1. 4. So when you do a matrix times its transpose, you always get a square matrix, right? Because this inner dimension is going to cancel out. We're always going to end up with the same on the outside. So we're going to end up with a 2 by 2. And so here's where a bunch of squaring goes on, right? 1 squared plus 3 squared plus negative 2 squared. 14. But we're not just squaring. I think we're just squaring on the diagonal. Is that correct? Go across here. I get first row, second column, I get negative 1 plus 6 is 5. Minus 8, negative 3.
Mm-hmm.
Second row, first column, negative 1 plus 6 minus 8. Same thing. And that should kind of seem reasonable. We're getting in our 2-1 position, we're getting the same entry as in our 1-2 position. But then when we do second row, second column, here we're back to sum of squares again, right? 1 plus 4 plus 16, 21. And we also need A transpose B. So notice we're just going to get a 2-entry column vector, right? Where did I got 110. So we want to solve 14, negative 3, negative 3, 21, x1, x2. Equals 110. This guy will be our x hat solution. That's what we're looking for. It's, and somebody told me they tried this ahead of time, it's real messy. It didn't really work to come up with nice numbers here. So this is very messy. And, but I got a unique solution. X1 is 17/95, X2 is 143 over 285. So what we call x hat, our least square solution, is just the column vector of those two matrices. Numbers are gross, so it's not too hard to picture. How do you know quickly that there's got to be a unique solution? Could you, like, if I gave you like a speed final exam, and I said in 5 seconds, tell me why we know there's a unique solution to that system. Time's up. You all fail. All right, yeah. So Amelia's looking at the columns, saying the columns are linearly independent of that little 2x2 matrix, because we got our shortcut when you only have 2 vectors. You could say neither one is a linear multiple, is a scalar multiple of the other. The other thing I was just thinking is the determinant is obviously not 0, so you can know real quick you can get the determinant. Because it's 2x2, right? If it were larger, it would not be so obvious. But so it's kind of an anticlimactic getting that fixed. But that's actually the closest vector to being a solution to AX equals B. This equation actually has no solution. Back on the handout, there's a little bit more. The length of B minus AX hat, so these are all constants, right? B is given in the original problem. X hat is part of our answer. This is the original matrix A. The magnitude of this is called the least squares error. Squares is, no, maybe it's, we'll just without an apostrophe. And the least squares error for this function. And here, the magnitude of B minus AX hat, well, the numbers, the fraction's already out of control with X hat, so I'm just going to give you a value here, is about 4.561 ugly looking decimal. So you can plug in, because this is constant 2x1. AX you have to compute. So we don't, AX hat, we don't have AX hat anywhere appearing in this calculation. So this you would have to compute. And it's a 2x1. And no, I'm not. B is 3x1. I'm losing my space. That's just the original B. Maybe I should write this down. AX hat is 3 by 1. So B is 4, 1, 3. Minus the matrix A, the original A is 1, 3, negative 2, negative 1, 2, 4. Times 1795, 143, 285. So again, this is 3 by 1. This is 3 by 2 times a 2 by 1 will be 3 by 1 also. So the length of that vector when you get through that calculation is just an awful mess of fractions. And this is called our least squares error. It's kind of a measure of how good the approximation is. The smaller that least squares error is, the closer you feel to actually having a solution. Yes?
So this is to me like something primarily some applications.
Yes.
So is that the case, or is there also like rich theory stemming from it, or like is it kind of developed?
Yes, but I don't know the details. I'm sure it's much more developed. So let's do our example, our theoretical example. We're just gonna move on to 6.6. I started teaching this course 2 semesters ago, and I had never learned this process before. Least squares from a linear algebra perspective. So I admit I'm fairly new on what this, it's fairly new to me what this whole process is. And what we're going to do is apply it to a situation you probably have already seen in another context. So an application to linear regression is called roots. I missed the whole middle. And there's one for it. Because we're finding the closest point in a given situation, it's like we're optimizing, kind of like you optimize in calculus, where we're minimizing the distance. I guess we're always minimizing in this situation because you're minimizing the distance between the B and the AX hat. Or you're minimizing the distance between the B and all the vectors in the column space of A. It's an optimization situation, and there's no calculus involved. So I think it's interesting how there's no derivatives being set equal to 0. It's just a geometry. You turn a problem into a geometric situation where you're trying to find, you have a given point, a subspace, and your solution is just going to be the closest point in the subspace to the given point that minimizes that distance. Now, this application 6.6 is probably one of the simplest possible applications of this least squares process. So have you done linear regression, or has anyone not done? So it's all explained here. It's just this idea that if you have a bunch of points in the plane, so 2-dimensional linear regression, they don't line up. We're trying to find the equation of a line that comes closest to those points. They don't line up. What does it even mean for an equation of a line to come closest to those points? Talk about that. we have endpoints, x1, y1, x2, y2, xn, yn, sitting in the x to y plane. We want to find a line that best fits these points. And we call that the least squares line. And because a bunch of squares will be involved in the calculation. So instead of y equals mx plus b, I'm going to go along with our book's notation and write the linear equation as y equals beta 0 plus beta 1x. I'm not a statistician, but they say that's what statisticians use. So just notice we've interchanged the order of the terms, so beta 0 is actually the y-intercept value, right? And beta 1 is the slope, so same as slope of the line, same as m. So beta 1 is m, beta 0 is b. I guess that's kind of nice because we've been using b for other things in our course. And so for each of our given data points, so the given data points are the simpler points here. So x1, y1 is 1, x2, y2 is another, x3, y3, they go on down the line. So here are the points not on the line in my picture are the given data points, or represent them. We are going to say x1 beta 0 plus beta 1 x1 is a point on the line we're looking for with the same x coordinate. But, well, the y coordinate might be different. The y coordinate is going to be given by plugging into beta 0 plus beta 1 x. So in each case, we have same x coordinate and a y coordinate obtained by plugging into the formula we're looking for. Now, if the points really lined up, what would be true is that the y coordinate here would equal the y coordinate here. So that's what this first equation is. The y coordinate here would equal the y coordinate here, second equation, and all the way down the line. So we have a system of equations where, how many equations do we have? So we have n equations, right? And how many variables?
2.
I got too many subscripts floating around. Do you know how many variables? There are just 2 variables.
Mm-hmm.
Yeah. So don't let the notation, make sure you realize it. So what about the x's and the y's? Those are all constants here. This is x1 is a number, y1 is a number, given number. x2 is a given number, y2 is a given number, all the way down the line. So that x sub n's to y sub n's are given numbers. It's the only unknowns here are beta 0 and beta 1. There are just 2 variables, right? So we have n equations and 2 variables. So we can write that. That's a system of linear equations in the variables beta 0, beta n. We have an awful lot of equations for just 2 variables. Chances are that system is going to be inconsistent because we got so many conditions on those 2 variables, right? Do you see? So here I could write, I'm going to call my beta vector the beta 0, beta. This is the unknown vector. Y, and now why did I say, capital X I got from the book. Capital X is just a matrix. Why the ones? Why do we write y x1, or 1x1, 1x2, 1xn? Just observe here that if I take this matrix x times that column vector beta, what it does is it just produces outputs that would look like my y1 through yn values, right? So just this notation is a little like, you're like, well, what the heck? X beta equals, what we want is x beta to equal y. So notice this is a matrix of constants. And it's n by 2. This is a constant column vector. by 1. And beta is, that's our variable in the equation. It's just a 2 by 1. Which one goes on top? Beta 0 goes on top. So this is new way to look at what we've been calling AX equals B in our standard notation, right? This funny looking X is just the A matrix. Beta is what we've been calling X all the way through this course. And on the right-hand side, what we're calling Y now is just the B vector. Right? So it's the exact same situation with just slightly, well, quite a different notation. Oh, I didn't realize that. Okay, so I could have just read this. Notice that X and Y are constants, the variables beta, and we want to solve for beta. But if the points do not line up perfectly, which is almost always going to be the case, then that matrix equation has no solution. It's inconsistent. So the best we can hope to do is a least squares solution, and we know what to write down for that. X transpose X beta equals X transpose Y. So this is the least squares equation that we can solve for beta 0, beta 1. And just I don't know, if you've ever taken a statistics course at lower level, they just sort of give you formulas and they don't really justify where the beta 0 and beta 1 come from. There is a way to do this using calculus, but it's kind of tedious where you do set up a function and take derivatives and set them equal to 0 and stuff. And this is just this beautiful little linear algebra application that tells us exactly, we know this will have a solution for beta 0, beta 1. And I don't think we'll get all the way through, but we can go ahead and start the observation. So you got to know this for our testing next week, this process. Either in the abstract, like we did in the previous section, or here where we're applying to one particular application. And this is the only application we're going to look at together. We're only going to do the linear regression situation. So I'm going to turn this off again. Okay. Any questions? Okay.
Yeah.
I didn't even bring this. I'm just going to have to watch my birthday. So we do have to kind of be aware of how to set up this problem. And I only have 3 points. That's pretty silly. Or 4 points, I'm sorry, 4 points. In a real application, you might have 100 points or 1,000 points if you're trying to find a line, right? So you're going to end up with quite an enormous system. And so my X matrix is going to be 1s in the first column with the X coordinates, the points 1, 2, 3, 4, 5, 6, 3, 1, 0, -4. You want to find finish this next time. We will do this on Wednesday. Just one little announcement about where we're headed. After we finish this nice application section, which I think you guys will have no trouble with, the 6.7 section is a little bit more, it is a little bit more intense. We're going to take our time with it though. 6.7 is about abstract inner product. So far for us, inner product means dot product of two vectors. Well, inner product can be defined in different ways. What about vector space of functions? What's an inner product of functions, right? What does it even mean to say that a function has a certain length or magnitude? So that 6.7 section is going to be a little bit more involved. We're going to be working with some functions, some integrals, some crazy theorems with abstract inner products. So I hope you